control flow, but also the arguments. And so what you're doing is you're returning to a location of memory, which is like the top of the function. And in essence, you're simulating a call to that function. Because when it accesses its arguments, it's going to read data that you control from the stack that you've overwritten. And you can chain these together so that you can call one function, another function, another function. The big difficulty here, though, is using the return value from those functions. It's not exactly like C code. You have to kind of do a couple things. But you can only do like a few hops, and have to do some tricks to pass values from one function to the other. But it's enough to have significant damage. Let's kind of go through quickly kind of how this works with some nice pictures. I tried to put as many pictures as possible in this presentation because I did a similar thing for RSA, and I had I think a third of my slides had pictures, and they still said not enough pictures. So I hope the pictures aren't overwhelming. So on the left here, I'm going to kind of show the assembly instructions that are getting executed. And on the right, I'm going to show basically how the stack is unwound and highlight in yellow the value that is being read. So first, we've overwritten the stack. We have a stack overflow, and we're executing the return instruction, which is going to use a value that we have chosen. And that's going to jump elsewhere in memory. And that's going to jump to the top of a function. And so it's going to save the EBP, save the frame pointer, and overwrite the existing return address. And importantly, later on in the function, it's going to access a argument. And it's going to come from the stack that we control, argument 1. And then it's going to reuse the saved frame pointer. And then it's going to return using another return address that we control. And this is going to be the address of a pop-pop-ret sequence, which will basically just advance past our arguments on the stack and then return to the next return address that we use. So basically, the pop-pop-ret pops off the arguments into registers because we don't really care what happens. We just want to skip past them, and then executes a return instruction using the address of the next function we want to execute. So that is how we use return chaining to chain returns to two different functions when we control the entire stack. So Return-to-Libc and return chaining are kind of the primordial ooze from which ROP was born. And this is enough to evade a good number of protections. Most notably, Scape and Skywing documented this technique to call NT-set information process, which would just disable dep for the entire process. So dep would be on, you just return there, turns off dep instantly, and then you return it to your shellcode. So done. And basically using return chaining is enough to do that. Also, this is enough to use the write process memory technique, which is, if you're on full disclosure, it was kind of interesting. Basically, it uses write process memory to patch the function itself so that it writes into its own code and then it starts executing from there. So it's a cool one-hop dep bypass technique. So after these kind of things, basically Microsoft had to react, and they reacted with permanent dep. So once dep is turned on, you can no longer just turn it off. Of course, if your application uses this feature. So if you're running IE8 on Vista SP1 and above, it'll use permanent dep. Otherwise, it won't. Or no, on Service Pack IE8 on Service Pack 3 and above, or Service Pack 3 will also use permanent dep. Otherwise, it won't. So again, it's this mismatch of supported configurations and a matrix on what mitigations you actually have and what actually work. So after permanent dep disabled some of these easy techniques, which the write process memory also gets past permanent dep, but it required attackers to up their game. And the response to this is return-oriented programming. And the kernel of the idea here is that instead of returning to functions or sequences of instructions, you return to arbitrary bytes that may or may not be the intended instruction, and you return midstream. So here in the, wow, it's a different color on there. You can see basically in the picture here, imagine you have the instruction move EAX on a 32-bit constant. That gets encoded into those 5 bytes that I show there. But if you return 1 byte in and only decode the last 4 bytes, it becomes the instruction sequence move EAX into ECX plus 8 and then return. So this is the main idea of ROP. Basically, you can find these instruction plus ret sequences anywhere in memory, and you can build them, combine them into something else. Or the best way to understand it, to credit Dr. Raid's girlfriend who thought of this, and we all think she's a genius because of it, is that it's like a ransom note. Return-oriented programming is like a ransom note, but instead of cutting out letters from magazines, you are cutting out instructions from text segments. which is basically exactly what it is. You're taking little bits, putting them together to have a higher order message. Build them into words and build that into the note. And in the terminology return to programming, these are called gadgets. You take kind of these useful sequences and combine them to a gadget. And a gadget is a high-level operation that is somewhat useful. So a gadget could be something like writing a chosen value to a chosen location. It could be modifying a value in memory, like adding or subtracting, logical operations, and so on, or calling a function in a shared library. So as an example, here's the simple gadget to do a write value to memory. If you have these three sequences, a pop EAX ret that sets EAX to a value of your choosing because it's reading all of this stuff from the stack that you control. You have a pop ECX ret, loads another register with the value you control, and then to the instruction move EAX into ECX ret. Basically, you can combine these three operations, and you have the gadget to write the value you choose to a location you choose. And just to kind of show how this works, we'll use my little stack diagram again. So we're starting out executing this code at the top that basically we jump to because we have control of the, of the stack. And then it's going to do a pop EAX, which is going to load dead beef, a value that we chose, into EAX. Now it's going to return again to the next location in memory of a useful sequence, which will execute a pop ECX, load feed face into ECX, and then it'll return to the third part of the gadget, which will move dead beef into feed face. So this is how you feed your face dead beef in return-oriented programming. And then it returns, which is not on the stack. And so it goes on to do something else. So you take these gadgets and you build what's called a return-oriented program. And you do this by scanning all of available memory for useful instruction sequences, and you kind of combine them into the gadgets. And then if you found enough gadgets to kind of form what Havav Shakam calls a gadget catalog, these are the kind of the core operations you need to have a Turing-complete language, you're done. And basically, you can actually use this as the backend for a C compiler. So in his initial paper, they actually wrote a compiler for this. So they compiled QSort to use only return sequences into libc. And it took like 1,000, 1,500 bytes, but it demonstrated that it was Turing complete, which is their big work. Again, what this shows is preventing the introduction of malicious code is not enough to prevent the introduction of malicious computations, because these random bytes in memory can be composed to achieve whatever the attacker wants. So what does the attacker want? To bypass DEP. So kind of give you a review of what DEP is. Hardware-enforced DEP uses the NX or XD bit of x86 processors to enforce the non-executable of memory. So on x86 processors, on the original ones, you could set the permissions. Like the operating system will tell you that a memory page has a readable, writable, and executable permission. And so most pages will be readable and executable, or will be just readable and writable. But if it's readable, it's also executable. And so what I call the NX and XD bits, I call it the I really mean it bit. Because if you don't set the I really mean it bit, being readable will mean executable. And that's even on newer processors. So you have to be in PAE mode and then set the I really mean it bit for the processor to do what you expect. And then, if that wasn't enough complication, that means that applications and operating systems may not get it right. It requires every application to be compiled with the NX compat flag. Otherwise, DEP will get disabled. Or it can turn it off dynamically, blah, 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 blah. So permanent DEP allows the application, like Internet Explorer, to say, DEP is on, I don't care what any ActiveX control says or does, or exploit says or does, don't turn it off. And so to get around this, we're going to use return-oriented exploitation. So I call these return-oriented exploits, which basically involves 3 steps. The first step is what I call the stack pivot, because the most important thing to control is the stack pointer. And like I kind of phrase this as ESP is the new EIP. Just getting EIP is not going to buy you much with DEP on, because you can't execute memory. So what you have to do is use control of EIP to get control of ESP, which you can then use to get control of EIP again. But the stack pivot step basically points the stack pointer into data that you control. And there's a variety of ways to do that. You find a sequence that will move a register that points to your data into ESP, or will adjust the stack pointer, add or subtract enough to point the stack pointer into something that you control. So if you control a string buffer farther up the stack, you can pre-populate that with your return-oriented program, and then point the stack pointer into it. Good to go. And so this